This video is going to review our unit on probability. If you're a student in my class, please pause the video, turn to page 57 in your packet, and work on the two problems that are there. Then unpause the video and we'll go over it. Okay, so number one says Miss Weese's candy jar contains 7 red M&Ms, 8 green M&Ms, 5 brown M&Ms, and 10 yellow M&Ms. If a student chooses 2 M&Ms without replacement, what is the probability that they will get different colors? So to do this the long way, which is what we're not going to do, we would do the probability of red and green, green and red. And then we would have to add to that the probability of red and brown. Like we'd have to go through all the different options. No one wants to deal with that. Really what we're going to do is we're going to consider what's not allowed, what we don't want. We want different colors. So we don't want the same colors. So if we find the complement of the probability of getting the same color, then we will have the probability of getting different colors. So this is what we're going to do. We're going to do 1 minus the probability of red and red, or plus the probability of green and green, plus the probability of brown and brown, or the probability of yellow and yellow. And again, these are without replacement, meaning we eat the M&M and that's going to affect the probability. So we're going to go 1 minus, we'll make a big bracket here. So if I get 2 reds is going to be 7 out of 30 times 6 out of 29. Then greens. Start with a fresh bag, 8 out of 30 times 7 out of 29. Oop, that's 9. 2 blues. Browns, sorry, why don't they have blues in here? Blue's the best M&M color. So we've got 5 browns, so 5 out of 30. Pick the first brown and then pick the second brown. Pick the first yellow, 10 yellows, 10 out of 30 times 9 out of 30, 29, sorry, we ate the first one. So if we put all of this in our calculator, now I didn't do the 1 minus first. First, I did all the fraction work, like the 7 out of 30, the 6 out of 29 plus 8 out of 30 times 7 out of 29. I did all that. And I ended up with 1 minus 0.23909, which gives me a final probability of getting different colors of 0.76091 or 76.1%. So now take a look at number 2. Complete the Venn diagram and use it to answer the questions. Students were surveyed and 30% are going to the prom, 50% are going to the baseball game, 45% are going to neither. Now I know that this whole diagram has to add up to 100%, so I'm going to keep that in mind. The first number I'm going to put in is 45% are going to neither, because that I know for sure. What I don't know is what percentage of kids are going to both the prom and the baseball game. So when I consider my 3 values, 30% going in the prom circle, including the overlap, 50% going in the baseball circle, including the overlap, and then the 45% that are going to neither, if I add those up, I get 125, which means I'm 25% over, and that must mean that 25% of the children are going to both. 30% minus 25, only 5% are going to prom only, and only 25% are going to baseball only. And now I can really easily see this is 50 and then this is 50. Now my percentages add up to 100%, and it's time to tackle the 2 probability questions. Letter A says, what is the probability that a student is going to the prom given that they are going to the baseball game? So probability of prom given baseball. So what percentage of kids are going to the baseball game? So as a reminder, when I'm looking at the baseball game, I'm only looking at this circle. I'm only looking at these 50%. So I have 50%. And then what percentage are going to the prom? Looking only in the green circle, I have 25. And if I divide that out, I get 50%. Half the kids, if I know you are going to the baseball game, think about it, that makes perfect sense. If I know you're going to the baseball game, you are 50% likely to go to the prom. Look, they're split equally. Letter B, what is the probability that a student is going to baseball or the prom? So if I'm going to looking at the probability of baseball or the prom, I need to think about that as these events are not mutually exclusive, meaning it's possible for them to occur at the same time. Now, I want to be really clear. You totally could just add up 5, 25, and 25, get 55, and be done. But if we're using the formula for not mutually exclusive events, it's going to be the probability of baseball plus the probability of prom minus the probability of baseball and prom. So the probability of baseball is 50%. The probability of prom is 30%. The probability of both is 25%. 50 plus 30 minus 25 is 55%. And again, this is just confirmed by adding up all the different options here, like 5, 25, 25, 55. All right. Are attending the prom and baseball independent? So I'm going to just call probability of prom is P. And I know the probability of going to the prom is 30%. I've already calculated the probability of going to the prom, given that I know you've gone to the baseball game up here, so I can recycle that. And that is 50%. And the answer is no, they are not independent events. Attending the prom and the baseball game, that's an M, are not independent because the probability of the prom does not equal the probability of prom given baseball. And I've stated those two values up there. So I don't need to remember this. Okay, so you have a test review. Again, I highly recommend that you pause the video and you work on the test review independently and then go back and watch the video once you have tried all the problems, because just watching me do the problems is not you understanding them. You are actually watching me understand them. So it's better to try them first on your own. Here we go. We have 6 pennies in a jar of 10 coins. 4 coins are randomly selected. Determine the probability that all 6 are pennies if you replace each coin. That means I take a coin out of the jar. I note that it's a penny. 6 out of 10 chances of getting a penny. Hey, look, I got a penny, and I put it back in. If I were to write this out, it would be penny and penny and penny and penny without replacement. So these are not conditional. So I'm just going to multiply and when I put that on my calculator, I get or about 13%. All right, so now determine the probability that all 4 coins are pennies. And now it says without replacement. So I'm going to slightly alter my calculation. If I were to write it all out, it would be like penny given penny at this point, like penny, probability of penny given penny. And then this one would be the probability of penny given 2 pennies. So let's go. First penny. All 10 of them are there. Now I reach in, there are 9 total coins, but only 5 of them are pennies. If I have 2 pennies, there are 4 left on the third selection out of 8. Then there are 3 left out of 7. When I multiply all this together on my calculator, I get 0.0714 or 7.14%. A pollster takes 100 subjects consisting of 45 Democrats, 30 of which are female, and 50 Republicans, 23 are, okay, so we need to create a two-way table for this data. So I'm gonna go, I'm gonna call this Democrats. You know, actually, I'm just gonna call it D for Democrats. That's way easier. We have D for Democrats and then not Democrats. We have female, oops, female and not female. We know that there are 100 people total. That makes life a little easier. 45 Democrats, 30 of which are female, of which tells me that this is going to be 30. And 55 Republicans, so we're gonna go 55 here. 23 of which are females, this is gonna be 23. So now with a little bit of subtraction, and addition, I know that this is gonna be 53, this is gonna be 47, this is gonna be 22, and 15, quick check. Wait, no, it's not, something happened. This is gonna be 30. Why, check. That's better. Okay. Find the probability. All right, so the probability that, I don't know why it says 2 each. I wonder if this was an old quiz and like 2 points each. That the subject is female. All right, so if I am picking a female, that is just going to be, I'm given that. Well, actually, no, I'm not. That's a lie. It's right here. It is just 53%. Find the probability that is a Democrat or male. So I'm going to grab a brighter color. So I'm going to look at these 4 more stratified values. Here are my Democrats. And then I also have the male Republicans. So I'm going to add them in. And when I add up those numbers, I get 77%. Now, another way to look at that would be the probability of being a Democrat plus the probability of being male minus the probability of Democrat and male, because we have an overlap. So the probability of being a Democrat was 53% plus 47% minus 15%. Wait, hold on a second. Democrat and, yep, that's right. So here we go. Oh, Democrat's the wrong number. I'm like, this is not going to add up to 75. My bad. Democrat's 45. So 45 for Democrat, 47 for not female, and then subtract the overlap, and I would still get 77%. Number 3 says the probability that the subject is a male Republican. So I can just look at my table. I have 32% are male Republicans. The probability that a female, so now I have a conditional statement, is a Democrat. So probability of Democrat given female, I have 53% are female. Of those 53% that are female, 30% are Democrats. And if I divide that out, I get 56.6%. Number 3, I have a spinner and I have a coin. And so I need to list all the outcomes. So I could go 1 head, 2 head, 3 head, 4 heads, 1 tails, 2 tails, 3 tails, and 4 tails. Determine the probability. So I'm going to make a note. I have 8 outcomes. The spinner shows a 3 and the coin lands on tails. Well, that's just one possible outcome out of the 8. The spinner is greater than 2, and I think this should say the coin. That would make no sense at all. The coin does not land on tails. So let's see. I'm looking for greater than 2, so 3 or 4, and not tails is going to be 3 heads, 4 heads, so 2 out of 8, and you are expected to reduce that fraction to 1/4. Are the events spin a spinner and flip a coin independent of each other? Well, I know they are because I know that spinning a spinner does not affect flipping a coin and vice versa. So what I need to do is I need to pick one event from spinner and one event from coin and show that the conditional will be the same. So I'm going to go with spinning a 1 and spinning a 1, given that you have flipped heads. So when I look at my sample space, there are 2 ways to spin a 1 out of 8, so 1/4. And if I only look at the heads, that's that top row, there are 4 outcomes, and one of them is heads. So obviously, they are the same. Yes. Spinning, can't spell. Spinning a spinner and flipping a coin. Please make sure you state the 2 events. They are independent, and our reason independent because their probabilities are equal. I don't need to restate that it's 1/4. They're both, the 1/4 is here. If for some reason I did not have this work off to the side, I would need to write after this statement equals 1/4. Researchers are looking at the relationship between cigarette smoking and lung cancer. And so we have a lovely Venn diagram and some probabilities to fill in. Let's get started. Smokes, 25%. So I'm assuming that's the whole smoking circle. That would make sense. Gets cancer, 35%. Again, that's the whole gets cancer circle. The smokers and the non-smokers. Does not smoke and does not get cancer. Okay, so that's definitely this outside region here, 61. And I know this all has to add up to 1. So I'm going to really quick add these up, and I realize I get 1.24. That means that there must be a 24% overlap. Probability is 24% that you smoke and get cancer, which means the probability of smoking and not getting cancer is only 1%. The probability of getting cancer if you are not a smoker becomes 14% by subtracting 0.24 from these 2 values. Find the probability of smoking and getting cancer. So the probability of smoking and cancer is the intersection of the 2 circles. I can't use the multiplication rule here because these are not, I'm pretty confident these are not independent events. It does not look like a proportional relationship. I have a Venn diagram, use the Venn diagram. The probability of smoking or getting cancer, I'm going to add up and I get 39%. Okay, now we've got a condition. So the probability, if you are a smoker, what is the probability of getting cancer? So first thing I need to do is start with a denominator of 25 because you have 20% chance of being a smoker. And then if I'm only looking in the smoker circle, you have a 24% chance. So that becomes 96% chance of getting cancer if you are a smoker. Okay, are the events smoking and getting cancer independent? Well, no, they're not. Right here, I've shown that the probability of cancer given smoking is 96%. Above, I was told the probability of getting cancer, what was cancer? Getting cancer is 38%. The events smoking and getting cancer are not independent because the probabilities are not equal to each other. Okay. probability of eating pizza for dinner is 20%. The probability of getting an A on a math test is 0.4%. Ben is happy when he has pizza for dinner and gets an A on his math test. Are these events independent? So I'm only given the probability of pizza and the probability of having a math test. And the question is, are these events independent? I'm going to go with yes. So what is the probability of having pizza and getting an A? Have to treat these like independent events. Again, there's nothing that I'm being told that if Ben gets an A, then someone's buying him a pizza. So I have to say the probability of having pizza and getting an A is going to be the probability of pizza for dinner times the probability of an A on the math test, which is just going to be 8%. Now, we've got a different situation. If the probability of A is 24%, the probability of B is 52%, and they are independent events, what is the probability of A or B? So I have to remember that for independent events, the probability of A or B, we will the probability of A plus the probability of B minus the probability of A and B. Because they're independent, I can just multiply these together. So I'm going to have 0.24, 0.52 minus the product. Toss that into a calculator, and you're going to get 6352. Or you could say 63.5%. Okay. Number 7 says, in a recent survey, 100 students were asked their gender and their class in school. If gender and class are independent, how many students should we expect to see labeled in box X? Now, I want to remind you something. Let's just pick male and freshman. If these are independent events, the probability of being a male will equal the probability of being a male given that you are a freshman. So I want to point out the probability of being a male is 40%. So I know there are 30 freshmen here. 40% has to equal however many males we have divided by 30. So if I just multiply the probability of being a male times 30, because they're independent events, I'm going to get 12. There are 12 male freshmen. And then that would mean that there are 18 female freshmen, and 18 out of 30 is 60. But we were only asked for X, but I find that it makes more sense if we do it this way. Another way to look at this problem is because they are independent events, the probability of freshmen is equal to the probability of freshmen and male, because they're independent, is the probability of freshmen times the probability of male, which is going to be 0.4 times 0.3. So the probability of freshmen and male would be 0.12. I have 100 people here. 0.12 times 100 again is 12. All right. I feel like we can all relate to the following situation. Take a moment and read the problem. We have a lot of information here. So the first thing we're going to do is create a tree diagram. The probability of having the flu is 35%. That means the probability of not having the flu, the complement of that would be 65%. I know that the probability that the probability that a student who has the flu also has a high fever is 0.90 or 90%, so it's fever. That means the probability of having the flu but not having the fever is 10%. So if I know you have the flu, the probability of having no fever is 10%. However, there's a lot of other reasons people could get sick. So this is no flu. If I know you don't have the flu, who doesn't have the flu, but does have a high fever is 12%. If I know you don't have the flu, you tested negative on the flu test, the probability of you still having fever is 12%. That means the probability of you not having a fever is 88%. Okay. Now that I have this organized, I can find the probability that a student at this school has a high fever by saying it's the probability of having the flu and a fever, or no flu and fever. So I'm going to go flu times fever plus no flu times fever. I'm going to toss that in to my calculator and I'm going to get 0.393 or 39.3%. Suppose I know you have a high fever. What is the probability that you have the flu? So flu given fever. Now, I can't read that right off my chart, but I know that from my formulas, the probability of flu and fever can be the probability of flu and fever divided by the overall probability of having a fever, which I found above, so that's handy. Now, this is a conditional statement, flu and fever. So it's not like the fevers cancel. I can't just rewrite this probability of flu times probability of fever. It needs to be 0.35 times 0.9, because if you have the flu, I know you have a higher chance of getting a fever, the overall probability of a fever. And so dividing that, I get 80%. The last question is going to be, what is the probability? Oh, sorry. Are having the flu and a high fever independent? So I know the probability of the flu. Why do I keep adding an E on flu? I know the probability of having the flu is 35%. I know the probability of having the flu, given that we have a high fever, because I just found that above, is 80%. So I'm going to say, no, the events having the flu. Why? No E, dummy. Are not independent. And again, I've stated them. This is part of my explanation. Because the probability of flu does not equal the probability of flu given fever.